damping, resilience, weight, resistance to wear, machinability, casting characteristics, and so on. Then we learnt about various standards and codes. Okay, and then we also learnt about the design process, right? So these are the things that we learned yesterday. Now coming to the next part of the problem. Okay, so we'll learn about basics of stress, strain, stress-strain curve, then the principal stresses, okay, and the equations pertaining to that. Okay, now let's learn what a stress is, denoted by sigma. What do you understand by stress? What do you understand by stress? Yeah, someone answer me. What is stress? Yeah, what is stress?
Sir, when an external force applied to a body, and then the body resists a force to that external force, that is called stress.
Okay. Anybody else? Anybody else? What is stress? Okay. Please look here. I have taken a body. Essentially, it's a spring, right? So for this body, I am going to apply load like this. So what's happening to spring? What is happening to the spring now? Yeah?
Expanding.
It is expanding or elongating, and it's also called deformation. Okay. Similarly, when I take a bolt and nut with washer, when I tighten the nut, the washer is subjected to deformation. Okay. Similarly, a shaft, when it is subjected to rotation, again it is subjected to deformation. Okay. So whenever there is load being applied, okay, there is going to be what? Deformation of the body. Okay. So deformation can be in the form of elongation, or it can be in the form of bending during transverse load. Okay, right? So now it can be twisting in case of torsional load, right? So the body will deform upon application of load, but the material of this member would offer a resistance against this deformation. That force of resistance against a deformation in this case is going to be elongation, correct? So the force of resistance offered by the material of the member against a deformation is called stress, denoted by sigma, and mathematically it is given by load by area of cross section. Load is in Newton, area of cross section in millimeter square. So the unit of stress is Newton per mm square or Newton per meter square. Is it okay? Next, what is the strain? What do you mean by strain? Denoted by epsilon. What do you mean by strain? Somebody please come out and tell me.
Ratio of deformation to the original.
Yeah?
This is the ratio of deformation to the original dimension.
Okay. So, as the spring, if I see, so this is the free length or initial length. When I elongate, there is going to be change in length. Okay. This ratio of change in length to original length of the member is called strain. Change in length can be delta L, original length can be L. Since both millimeter cancel out, it's going to be dimensionless. So what is it according to Hooke's law? What is according to Hooke's law? We have, according to Hooke's law, we have Young's modulus is equal to
stress upon strain under elastic limits.
Yeah, that is stress is proportional to strain within elastic limits. Correct? That is stress is proportional to strain within elastic limits. Taking out the proportionality, what I am going to get is I am going to get a constant that is called Young's modulus, that is given by ratio of stress to strain Again, strain has no dimensions, stress has got Newton per mm square. So the same dimensions will carry for Young's modulus as well. Is it okay? So this is stress, strain, and then Young's modulus, which is the ratio of stress to strain, okay, within elastic limits. Then we learn about the stress strain diagram. Okay, is it visible now for you? Is the stress strain curve visible?
Yes, sir.
Okay. So I take a member, then subject it for loads. This experiment we have done in our material testing lab using UTM. Okay, so we apply the load, keep on applying the load using so initially what we do is we take the gauge length of the specimen, then hold it in UTM, and then apply load axially. For every load that we apply, we are going to note down the change in length or elongation of the specimen. Okay, so we know the original area of cross section, we know the load applied. So each load we are going to get stress values given by P by A. And using, what is the instrument that is used for measuring the deformation in UTM? Which instrument did you use? Do you remember? What instrument did we use? Yeah?
UTM, sir.
Yeah, UTM is the machine to measure the deformation or change in length. Which meter that we used? We used extensometer to measure the change in length. So we noted down the change in length delta or delta L. We knew the original length, that is the gauge length. So delta L by L will give us strain. So with various loads, we know the original area of cross section of the specimen. We know the original length of the specimen. So using extensometer on UTM, we are going to find out deformation delta L. So we can get stress and strain values. Then plot the stress strain values. Okay. So for a ductile material, we are going to get something like this. Correct? So here is the proportional limit P, then comes elastic limit, which are more or less very, very close. Then the upper yield point, this is the lower yield point. So I would say sigma y, L, sigma y, U there. And what is this value? What is this value over here?
Ultimate
Stress, that is sigma U, this is sigma y, and then this is going to be fracture strength. Correct? That is sigma B, or I would say sigma F. So that's going to be fracture strength. Okay, where it's going to fracture. This is the stress strain curve for a ductile material. Okay, this is the proportional limit, elastic limit, upper yield point, lower yield point, ultimate strength, and breaking strength, fracture or breaking strength. Okay, and here we have got two divisions. One is the elastic region and another is the plastic region. Okay, this is the plastic region where it cannot regain its original shape and size. Okay, then this is the what? This is the elastic region. Correct? This is the elastic region within which, when load is removed, the material will regain its original shape and size. This is stress strain diagram for a ductile material. Now, what is it for a brittle material? So stress along y-axis, strain along x-axis. So for a brittle material like glass or cast iron, okay, so there is no yielding taking place. So the material will break. So it will have the breaking or fracture strength. Okay, breaking or fracture strength only. So it does not have any yield. So this is the stress strain diagram for a brittle material. This is the stress strain diagram for a ductile material, wherein you have got elastic region and plastic region, and Here there is no yield taking place. Are you all there with me? Are you all there?
Yes, sir.
Yeah, please note down the stress, strain, then Hooke's law, and then note down the sketches of stress strain diagram for ductile material and stress strain diagram for brittle material. Please note down in your notebooks. Finished, huh?
So 1 minute.
Yeah. Small correction. Small correction. This is elastic region is up to yield point. Sorry. Okay. This is elastic region up to yield point. After that only the plastic region starts. Please make correction there. Okay. Up to yield point, it is the elastic region. Then beyond that is plastic region. So anyway, elastic limit is indicated by E there. Please note down. Please note down. For ductile materials, yield stress for ductile materials yield stress sigma y should be taken as a reference. For ductile materials, yield stress sigma y should be taken as reference for designing a component. For ductile materials, yield stress sigma y should be taken as reference for designing a component. Designing in the sense we are going to determine the size of the component. Okay. So, and material as well, right? So, for ductile materials, yield stress should be taken as the reference for designing the component. That means the maximum stress induced, okay, should be less than or equal to yield stress of the material, okay, for safe design. Please note down. Please note down. That is, maximum stress induced should be less than the yield stress of the material for safe design. That is, sigma max or sigma induced okay, because of applied load, or sigma induced should be less than the yield stress of the material. For ductile materials, yield stress should be taken as reference for designing the component or machine component. That is, the maximum stress induced should be less than the yield stress of the material. Okay. Next, note down. For brittle materials, for brittle materials, ultimate stress sigma u, ultimate stress of the material should be taken as reference. For brittle materials, ultimate stress sigma u should be taken as reference for designing a component. That is, the maximum stress induced, or the sigma max, or the stress induced in a component or in a material should be less than the ultimate strength of the material in case of brittle materials. Is it okay? Finished down? Noted down?
Yes, sir.
Okay, done. Yeah. Now, let us look at the principal stresses and principal planes. Right now, that is principal planes and principal stresses. I have studied this topic in mechanics of materials, principal planes and principal stresses. I have studied. Yeah, one of you please interact.
Yes, sir.
Yeah, don't worry if you say yes also no problem, no also no problem. Okay, you have studied, correct? Right. So what have you understood? And why we have to study principal planes and principals? Why should we know principal planes and principal stresses? Why should we know that? Yeah, any idea? Tell something, even if it's wrong, not an issue. Why we should study, why should we know principal planes and principal stresses? Yeah? No idea? Please say yes or no. No also is okay. Someone should say no, at least.
No,
No,
sir.
okay, that's fine. Yeah. Now, when we take a member, I just take a member, subject is to axial, tensile, load, fee, something like this. Okay, I will subject this member to an axial, tensile, or something like this. If I have to find out the normal stress, that is, I take a section plane perpendicular to, that is, I have a member I subject this to elongation. So to find out normal stress, what I do is I take a section plane perpendicular to the axis of this member. Okay, are you there with me? I cut this perpendicular to the axis of the member, like which is subjected to elongation, something like this. Okay, when I take a section plane, okay, so the stress that is induced, we have two stresses induced, one perpendicular and another parallel to the plane. So perpendicular to the section plane, we call it as normal stress. Parallel to the section plane, we call it as tangential stress or shear stress. Are you with me? Are you with me?
Yes, sir.
Yeah?
Yes, sir.
Yes,
There
sir.
are certain members which are subjected to transverse load. Again, we use equation bending stress is equal to m by z, which will give us the bending stress on the plane. Then we have a member which is subjected to torsion, something like this. Okay, T and T dash. What we are going to get is shear stress given by 16 by pi d cube after simplification. Okay, so these are all the basic equations. So here I am going to get sigma that is given by T by here. Correct? But in practice, all the components are subjected to combined axial bending and torsional loads. You take bearing, you take propeller shaft, you take gearbox shaft, okay, any example you take, they are not subjected to only axial load or only bending load or only torsional load. They are subjected to a combination of these three forces. Okay, that is axial force, transverse load, and also torsional load. When it is subjected to combined loading like that, okay, if we take a plane which is perpendicular to the axis, we may not get the actual maximum stress induced on the component. Say I take this member for example, this is subjected to torsion as well as axial load. When I take this member, combined loading, if I take a section plane perpendicular to the axis, I will not be able to get the maximum stress induced in this member because of the loading system, which is transverse load, axial load, and also the torsional load. Is that okay? So in such cases, there are certain planes which will give us the maximum stress induced. Okay, so we are going to get sigma max, sigma minimum, and tau max. Okay, there are certain planes where there is no shear, presence of no shear stress. Okay, such planes are called principal planes. The stresses acting on such principal planes are called principal stresses, which will give us the maximum stress induced because of combination of loads. Are you with me? So those planes are not the normal planes that we have taken over here. It can have any orientation. It is our job to find out the orientation of such principal planes and on which the maximum principal stress are going to act. So this maximum stress, because of combined loading over there, okay, should be less than yield stress in case of ductile materials for the design to be safe. If I just take normal plane, that is plane perpendicular to the axis, I will not get the maximum stress. So I have to find out planes which will give us the maximum stress induced because of combined loading on the component. Okay, so those stresses are called principal stresses. And the planes which have got zero shear stress are called principal planes. Are you with me? Are you with me? So the total essence of learning principal planes and principal stresses is to find out the maximum stress induced in a member which is subjected to a combination of loads which can be axial, bending, and torsion together. Are you there with me? Are you there?
Yes, sir.
Yes, sir.
Now we need to know the sign convention before we get into the problem. So what I do is I take a small element from this member, okay? So this is a small element that I am going to take from any member. It can be ship hull or aerostructure. I'll just take a small element of the member which is subjected to, so this is sigma x along the x-axis, sigma x. So we are learning about sign convention, okay, before we get into finding out principal planes and principal stresses. This is x-axis, this is y-axis. So load along the x-axis is sigma x, this is sigma y, this is tau xy. Okay, so when you have a system, something like this, so sigma x, which is shown going outward, we take sigma x to be positive. It's a positive value. Sigma y is going towards the element, so sigma y is negative. And for tau xy, to the right of the element, if it is acting upward, then we take that as positive, otherwise negative. Is that okay? So whatever I have shown here is a small element, okay? Small element of an aircraft structure, or it can be a small element of a ship hull, right? So it's subjected to a system of stresses, sigma x along x-axis, sigma y along y-axis, and tau xy on the surface. So if it is acting out away from the element, it is taken as positive. If it is acting towards the element, then it is taken as negative. And the shear stress is positive if it is to the right of the element and acting upward, that is taken as positive for finding out the stresses. Are you with me? Are you with me?
Yes, sir.
Yeah, please note down the sign convention sketch over here and these details.
Sir, could you give a definition or something for principal plane and principal stresses?
Yeah, note down please. Please note down. Practically, most of the machine parts are subjected to. Practically, most of the machine parts are subjected to. Practically, most of the machine parts are subjected to several types of loads simultaneously. Several types of loads simultaneously. Several types of loads simultaneously. Example, a transmission shaft. Example, a transmission shaft. Or a shaft in a gearbox. Or a shaft in a gearbox. Or a shaft in a gearbox. Is subjected to bending moment as well as torsional moment at the same time. Bending moment as well as torsional moment at the same time. Say suppose if you take a shaft in a gearbox, so it will be mounted between bearings. So on this shaft you will have gears mounted. You will have numerous number of gears mounted, and in turn they are onto some other shaft something. So when you have shaft mounted with gears like this, right? So it is subjected to, and also it will rotate. Okay, it will rotate in the bearings. So shaft is rotating along with the load in the form of gears on the gearbox shaft. So it is subjected to both torsion and bending. Okay. Yeah. What we have taken now? What we have taken?
Bending moment as well as torsional moment.
Torsional moment at the same time. at the same time. Full stop. It is necessary to determine. It is necessary to determine. It is necessary to determine the maximum value of normal and shear stresses. Maximum value of normal and shear stresses. Maximum value of normal and shear stresses, so that they may be compared with, allowable value of stresses, allowable value of stresses, sigma y or tau y, that is yield shear or yield stress. Next line. Next line. It is important to determine. It is important to determine. It is important to determine the planes which carry. The planes which carry. The planes which carry maximum direct stresses, maximum direct stresses, and maximum shear stresses, maximum shear stresses, when a system of forces are acting on a body. When a system of forces acting on a body. Next. Next line. The planes which carry, the planes which have, you can take that way, the planes which have, the planes which have, the planes which have no shear stress, the planes which have no shear stress, the planes which have no shear stress are called principal planes. The planes which carry no shear stress, the planes which carry no shear stress are called principal planes, are called principal planes, and the stresses acting on such principal planes are called, and the stresses acting on such principal planes are called principal stresses, are called principal stresses. Are called principal stresses. You can take one more, come to next line, come to next line. The same thing in a little more easier way, okay? In most cases, direct stresses, direct and shear forces rather, in most cases, direct and shear forces act simultaneously on a body and the maximum value of resultant stress may act in some other direction other than that of load application. It is therefore necessary to find stresses on planes other than those of load application. Other than those of load application. Okay, finished up? Finished writing?
Yes, sir.
Yes, sir.
Okay, so basically, when you take a member, you have three mutually perpendicular planes, as I said. Okay, so one will give you maximum direct stress, another will give you minimum direct stress. So that's what we have just now taken. Okay, so this will give you the maximum direct stress, and this will give you minimum direct stress, right? So the planes are called the principal planes. So this, if I take as theta P1, this is theta P2, they are at 90 degrees to each other. Okay, this principal plane 1 and principal plane 2, okay, they are at 90 degrees with each other. If I find out theta P1, that is the position of principal plane 1, okay, and this is the position of principal plane 2. So they will be at 90 degrees with each other. And we have got what are called as shear planes. Okay, so where you will get the shear values, they are at an angle of 45 degrees with reference to theta P1. You will have theta S1, and again theta S1 and theta S2 are at 90 degrees with each other. Is that okay? Right? So theta P1 and theta P2 will give you the position of principal planes. Theta S1 and theta S2 will give you the position of shear planes. Okay? And theta P1 and theta S1 are at an angle of 45 degrees and theta P1 and theta P2 are at orthogonal to each other, and also theta S1 and theta S2 are again perpendicular to each other. Is that okay? Is that okay? So theta P1 and theta P2 are called principal planes. They are the principal planes, whereas theta S1 and theta S2 are called shear planes. Please note on this. Please note on this. Hey, don't spend typing in the chat box. I say no point in typing those years in there. I'm not going to take that. Okay? Don't keep typing your USN in chat box. Did you finish with this? Finish noting down?
1 minute.
So in that cube that you've drawn, sigma max, and what are the other two, sir?
Sigma max, sigma minimum. This is tau max.
Okay.
Maximum direct stress, minimum direct stress. That will be principal planes 1 and principal plane 2. Have you tried to obtain a data handbook by some means? Could you people get data handbook?
So we have soft copy of it.
You have soft copy, no? All of you? How did you get this soft copy, Siddharth?
Sir, actually Karthik had shared it in the group, sir.
Oh, is it? Okay. So all of you possess data handbook then. Where you shared?
In the unofficial group, sir. I'll share it in the official if you want.
Yeah. Please share it. Please share it to me. Otherwise, others, have you taken? Sai Sumant, Abhishek.
Actually, it is having 1300 pages, sir.
Yeah?
Siddharth will share it now, sir.
Okay. Please take that. Please take that. Okay. And keep it with you from tomorrow onwards. You need data handbook. Okay. Yeah. Sign convention. You have taken down sign convention sketch there?
Yes, sir.
Yeah. Positive normal stress act outward. Please take that. With reference to sign convention, please take positive normal stress acts outward. Positive normal stress act outward from all the faces. Positive normal stress act outward. Positive normal stress act outward. So that means here sigma x is positive. Okay. And this is negative. Sigma y is negative. And positive shear stress, positive shear stress, positive shear stress acts upward on the right face of the element. Positive shear stress act upward on the right face of the element. Is that okay? Did you finish noting down?
Yes.
Okay. So in today's class, what all we learned is about stress, strain, Hooke's law, stress strain diagram. Then we learned about the principal planes and principal stresses. Then we learned about sign convention. Okay. So tomorrow onwards, we are going to get into uniaxial stress system, biaxial stress system, triaxial stress system. Okay. And the problems pertaining to that. So by tomorrow, you are expected to go through the initial 5 or 6 pages in the data handbook. Okay. To come with knowledge of what is normal stress, what is tangential stress in an uniaxial stress system, what is normal and tangent stress in biaxial stress system, and so on. Okay, it will be easy for you to follow. Are you with me? So open the data handbook. I think Siddharth will share data handbook to me also. Okay, it is what edition you have, Siddharth? Which edition?
Sir, it is K. Lingaya second edition, sir.
Oh, it's K. Lingaya, is it? No. Then don't use that. We'll go with Balvi Reddy Mahadevan. If you get Balvi Reddy Mahadevan, don't share that with any of your friends. Okay?
Okay, I'll delete it.
Yeah, I delete it.
Can you share it with us, sir?
That's what. I don't have soft copy of Balvi Reddy Mahadevan. So I'll try to take PDF of that in our library and try to share whatever that's required. I'll try to do that. Okay. Don't refer K. Lingaya data handbook because that is 2 volumes and it is too bulky to handle and it will not be given in examination in our thing. So what we provide is Balvi Reddy Mahadevan data handbook. I will refer that. Okay. So all of you, please switch on your videos. Please switch on your videos. What Abhishek Narayan noted down today?
Yes, sir.
Huh?
Yes, sir. Yes.
Sincerely noted down or trying to cheat?
No, sir.
You don't need to cheat me, okay? There's no use. Anyway, yeah. Sai Sumant, switch on your videos, please. Sai Sumant.
Yes, sir. Present, sir.
Okay. Abhishek GL.
Yes, sir.
Switch on video, man. I tell you several times. Abhishek GL is there.
Yes, sir.
Show me your face. Abhishek GL.
Camera is not working, sir.
Show me your face.
Camera is not working properly, sir.
Why you are absent from last 2 classes?
Last 1 class only, sir.
Last 2 classes you are absent. Yesterday you were there.
No, sir. Yesterday I am not there.
Day before yesterday?
Present, sir. There, sir.
No. Abhishek Narayan.
Present, sir.
Adarsh Desai.
Present, sir.
Ajay Sunil.
Yes, sir.
Hey, how many times? Yeah. Switch on videos. I say Akram Anwar.
Present, sir.
Adarsh Desai, you can go off the video. Akram Anwar.
Present, sir.
Akshay Jadhav.
Present, sir.
Mundiar,
Present, sir.
Nambiar,
Yes, sir.
Nadella,
Yes, sir.
Deban,
Present, sir.
Chinmay, Chinmay Prasad, yeah. Okay. Chandan Swarup, Chandan Swarup, Charishma, okay.
Present, sir. Chandan Swarup.
What? Chandan Swarup,
Yes, sir. Yes, sir.
Who is Chandan Swarup? Please come on camera.
So 1 minute, sir. It's not open. Some error. It's
No, I don't agree. Darshan,
Present, sir.
okay. Ibad Kausar,
Present, sir.
Ibad, okay.
Present,
Going
sir.
on.
Present, sir.
Chandan Swarup has come? No. Jayant Reddy,
Present, sir.
Purushottam Reddy, Purushottam Reddy, Ritik Shah,
Yes, sir.
Jay Bansali,
Present, sir.
okay. Jitin Kumar,
Yes, sir.
okay. Chaitanya Vamshi, Chaitanya, Karamjit Singh,
Present, sir.
where were you for so long, man?
Present,
Where were
sir.
you?
Actually, sir, I am having only 2G net in my place. I am not able to see video
Which,
properly, even though my video call is cutting again
which
and
place you stay?
Sir, I am staying in Jammu and Kashmir.
Okay. Right. Avasti. Kiran V. Mastanullah.
Present, sir.
Mazin Omar. Sharan. Narendra. Niyal Shetty.
Yes, sir.
Nikhil. Vagmesh. Nitin.